Okay, so I would like you to explain our code here, starting from the top. So we wrote some code off screen. So what does it do? What is trials?
Trials is the number of series of rolls we're doing.
Okay. Including the ones that don't
work. Yeah.
All right. So rolls. What is rolls?
Rolls it's keeping track of the number of rolls it took.
Okay. So rolls is a table.
It's like table in the first spot. That's like how many times it took one roll, and the second spot's how many times it took two.
Yep. Very good. Length.
Length is the amount of rolls it took. It's just a variable for that. And then success is a variable for how many successful trials we had.
Okay, very good. All right, so now let's scroll down a little bit. So we make a little for loop for I equals 1, I less than trials. What's that doing?
It's just running a lot of trials. It's running one less than the number of trials.
Good point. You should make it less than or equal to. That's fine. And then what's this inner loop going 500? What are we doing 500 times?
So we're rolling the die 500 times.
Okay. And why did we pick 500 as the stopping point?
We're never.
Yeah, just put a space.
We're never going to reach 500 rolls because that's near impossible to do.
Yeah, we don't think we'll ever continue for 500 times. But we could have made this 5,000 if we wanted to be super safe. All right. So then we pick a random integer. Oops, I rolled that off screen. What does random integer 1 to 6 do?
It's rolling a die.
Okay.
A six-sided die.
All right.
If it's an odd number, we start over by setting j to one more than the number of.
Done the inner loop.
Yeah.
Okay. And what's going on here?
If it's 6, then the length variable goes up by the amount of trials it took, j.
By the number of rolls it took.
Rolls.
Yep.
And then we input j into the rolls table. We put the number of rolls it took.
Yeah, so if this one took 3 rolls to see the 6 for the first time,
spot.
we increment the third spot. And then what does success plus mean?
That's the number of successful trials.
And then j equals 501. What does that do?
Stops the loop.
Stops our inside loop. And that's it. And then at the end, what we're going to do is we're going to output length divided by success. So the total sum of all the lengths divided by the number of successful trials. So that should give us our average number of rolls. Rolls 1 divided by success. What should that tell us?
So that's the number of trials where we got it on the first roll.
That's the number of successful trials where we got the 6 on the first roll. And then histogram of rolls. What's that going to show us?
It just makes a table or a graph of all of our rolls.
Okay.
So distribution.
So we did it 100 times to make sure everything was working, but now we'll just run it 1,000 times and you'll see it or 10,000 times and you'll see it for the first time.
We get pretty close to 1.5.
Yeah, although what's happening here?
Did we switch the axes by mistake?
Yeah, why did we have something going out almost 200 times? That doesn't seem right. Come back to that in a minute. But the average number of rolls?
About 1.5.
Yeah.
1.5. The average number of trials on the first time? So we had 6 on the first time?
So about 2/3.
So it's 2/3 kind of what we were seeing. Now let's see what we did wrong.
I think the axes are just flipped because there's only 15 things. Like the top number of things is 15, and we definitely had more than that.
Yeah, so rolls is a table. Oh yeah, geez. Sorry, it's not. We don't want a histogram of rolls. We want a list plot. There we go. And even this is difficult to see because the number of times with 5, the number of times it took 5 rolls, it looks like it was about maybe, 30 times.
Mm-hmm.
But we can see how frequently it was on the first.
They're off
Goes
the
up
screen.
really really fast.
Yeah, so that's interesting. So maybe we should actually, instead of just list plotting it, we should just print the first couple of ones. So here's how often we're getting it on the second time. Here's how often we're getting it on the third time. Okay.
So
It drops off
decreases
really
a lot,
fast.
So roughly 2/3 of the time.
like we thought.
Can you recognize what this probably is? 0.228639? Do you recognize a decimal that's near to that?
It's close to a fifth, but not all that close.
It's somewhat close. No.
Not
Maybe
sure.
2 nines.
Maybe 2/9. Let's do, instead of 10,000 trials, maybe we can do 1,000,000 trials. Hopefully that won't take
that
super
long.
long. There we go. Okay, so again, about 1.5.
Total.
We recognize that 0.667 as being roughly 2/3, and so
It looks like it's 2/3 divided by 3 almost.
So
It looks like we're almost dividing by 3 every time because
2/3, 2 nines. So then it'd be-
aha. So we're almost dividing by 3 every time. So maybe we actually have a geometric series that starts with 2/3. Then this would be
2 nines.
This would be
2/27s.
2/27. So let's see if we can make that hypothesis. So we'll multiply this by 9 halves, and we should get a number close to 1. We'll multiply this by 27 halves, and we'll get a number close to 1, we think. And then to test our hypothesis, let's multiply the next one by 81 halves.
Okay.
And it's going to be n rolls 4 divided by. So there's how often it goes. So we expect the outputs now to be about 1.5, about 2/3, and then 1, 1, 1.
Yeah.
And again, remember, this is 1,000,000 trials. So let's see.
Yeah, very close to 1.
So good job, good spotting that we were roughly dividing by 3 every time. So we see 2/3 of the time we get a 6 on the first roll. Then it was 2/9 on the second roll.
2/27.
2/27. It falls off super fast. So it's a geometric series with a factor of 1/3. And then trying to figure out why that factor is 1/3 every time is actually a pretty fun challenge. But maybe we can do that in a later project. Okay, so are you surprised on this that it's shorter?
Yeah, it's definitely sort of seems similar to.
It seems similar to the first problem where the answer is 3, and here it's actually 3 halves. So it's cool. It's a neat problem, and it shows you how subtle probability is. All right, good job, guys.